Hello, everybody, and welcome to the 8th session of the RQI 2020-2021 online. And this is a slightly special one because we are under daylight savings time here in North America, but not in Europe, which means that attendance today may see a spike at 10 a.m. I don't know, but then just something amusing to look for if you if you want. The first speaker of this session is Kasia Resner. It's my pleasure to introduce her. She's a professor at the University of York, and she's going to talk about locality and causality in quantum field theory. Kasia, floor is yours. I'll give you a 5-minute warning, and whenever you want.
Thank you. Thank you for the invitation, for the opportunity to speak here all the way from England. So I would like to tell you something about notions of locality and causality in quantum field theory. Well, maybe there's something new, but mostly just to give an overview from algebraic quantum field theory perspective. Okay. So first of all, I want to talk about locality, and then I will talk about non-locality if there is enough time. My favorite approach to quantum field theory, as some of you might know, is algebraic quantum field theory, and I want to bring it everywhere I can. So in particular, I use it for quantum field theory on curved spacetime. And it's actually quite convenient to use it that way. It solves some of the usual conceptual problems of QFT on curved spacetime. And here I list some people who contributed immensely to developing that framework. So Hollandswald, Brunetti, Frenhagen, Feich, Chris Fuster. Also, I should probably mention my colleague from York, Bernard Kay. Many, many more people. So this is a big, big field that's still under development. So the main idea is that, first of all, it is a generalization of algebraic quantum field theory, which dates back to the 60s to ideas of Hart, Kastler, and Araki when they essentially designed that to study QFT on Minkowski spacetime. So this is where things started. So the idea is to encode all the physical information about the system in assigning algebras of observables to regions, essentially bounded regions in spacetime. So here is a cartoon. So you have a region M in N, and you assign to it an algebra A of M. And the advantage of that is that, these algebras can be studied independently of a concrete Hilbert space representation. So you can separate the problem of understanding defining observables from the problem of thinking about states and representations. And usually when you start thinking about Hilbert space representations and states, things get necessarily non-local, whereas when it comes to observable, you can actually raise that question, can you have locality or not? So I'm going to focus today on the observables and try to approach the question of locality or lack thereof on the level of observables. Okay, so first of all, first local thing is the local covariance. And this is a very general feature of this framework of algebraic quantum field theory on curved spacetime, is that if you have embedding of a smaller spacetime into a larger spacetime like that, then you want also to have the embedding of corresponding algebras like that. And also, if you have the embedding itself, you assign to it a map of algebras. And if you are mathematically inclined towards category theory, then you might use a fancy word that this assignment is factorial. If you don't like that language, then you can just say, well, it's as covariant as it gets. So it's compatible with the structure of embeddings. So that's the basic setup. And now locality. So there are different things that people mean when they say locality. And let me, single out 3 of those in QFT, or in particular in algebraic quantum field theory. So first of all, is something which I would rather call localization, which means that you can actually assign observables to bounded regions. So this kind of captures some of the meanings of locality. Second, it has something to do more with the type of interactions you want to consider. So locality in the sense that interactions are point localized, so as we are used to in particle physics. And classically, in classical field theory, this means that we use local functionals to describe those interactions. And finally, there is locality as causality, which here I have a cartoon. If I have two regions O and O prime, which are space-like separated, then I expect the observables assigned to these regions to commute. So this is yet another way that people understand locality in AQFT. Okay, and now let's break those notions of locality. So the first one is easily broken. So the question of localization in bounded regions, well, already in sort of canonical AQFT, this goes wrong sometimes. So if you have long-range interactions like QED, then things cannot actually be localized in nice bounded regions. So a fancy way of saying it is that charges are not localized. And there are also other better ways of localization, which are more suited for long-range interactions, for example, string-like or cone-like localization. So this is kind of well understood by now. So that type of localization can be described. The second type of locality, interactions being point-like, this can also be broken. And well, I mean, sometimes you just need to use non-local interaction, either for your original theory or for the effective theory you get at in the normalization process. And in the very extreme case, which I want to discuss in a minute, if you consider quantum field theory on something like a causal set, then the kind of interaction you get is very highly non-local. So this type of locality gets broken. But the third one actually survives quite long. So locality as causality, it can be obviously implemented also for things that are string-like localized, and also makes sense if we go in the very extreme situation where we will replace the spacetime with a discrete poset. So this is the causal set setting. There you can also make sense of local covariance, and you can also make sense of locality as causality because you have causal structure. And this has been described in my paper with Edmund W. Heath, Chris Fuster, and Nick Woods in PhysRevD, where we explored that possibility. But it fails, the third type of locality, it fails if observables have to be localized in all of M, because if you cannot really talk about the causal complement of a given region, if you cannot really find something which is space-like to it, if the observable is localized in all of M, then clearly you cannot have this type of locality. And this kind of unfortunate situation is expected to be true in quantum gravity. So there you have to give up, the last notion of locality that stands. The good news is that some of the methods for constructing AQFT models that I'm going to describe in the rest of this talk actually work also when that notion of locality is broken. So you can break a lot of locality and still be able to use some of the AQFT or PAQFT methods. P stands for perturbative. Okay, so now let me just give one more disambiguation about this locality and causality. So in the literature, we typically call it Einstein Causality. So this is the third type of locality. And this is actually independent from the notion of there being or not being a time evolution. So these are separate axioms in algebraic quantum field theory. So here, causality really means just independence for regions that are space-like, so observables which are localized in space-like regions commute. So this is the principle of special relativity, that nothing can move faster than light. But there is also, a different notion of, causal order, which is related to the time direction. So you can have causal structure and not have a preferred time direction, which is usually the case. For example, if you give up some of the usual manifold and space-time structure, if you are on the causal set, then you have causal relations, but you don't have time direction. Time direction is related to another axiom, which is the time slice axiom, which means that if you have the algebra associated to a neighborhood of a Cauchy surface, this is then isomorphic to the algebra of the whole region or whole space. So this is the QFT version of initial value problem and time evolution. So time evolution is a sort of separate issue from Einstein causality. And I'm not going to talk about it anymore, but just to make that little disambiguation. Okay, so now I want to spend the rest of this talk talking about a very concrete way of constructing models in algebraic quantum field theory, which is perturbative algebraic quantum field theory. And this combines the ideas of, this having the net of algebras assigned to regions, or, algebras assigned to spacetimes, but we allow to use also formal power series. So we allow perturbation theory to come in and help us, which is very beneficial if, we actually want to describe physical things like the standard model or QED, because they're, we don't really know much beyond the perturbation theory, at least in 4 dimensions, which happens to be the kind of, number of dimensions we have. So I have to deal with it. Let me mention some names again. So, there are several stages in that procedure. So one is about the formation quantization of classical Poisson algebra of observables. And there, I would like to mention Brunetti, Frenhagen, and Deutsch in various configurations, mostly in 2000s. As far as interaction goes, I'm going to talk about it more later. This uses Epstein-Glaser framework, which is slightly older than the rest of the formalism, goes back to the 70s. And finally, gauge theory's generalization is surprisingly recent. So the first work was done by Holland in 2008, and then there was my work with Frenhagen in 2011. So this is, just a brief overview of the progress of that field. And if you're interested in learning more, there's the review I wrote, Perturbative AQFT, Introduction for Mathematicians. If you're not mathematicians, you can still read it, it's just kind of trying to be mathematically rigorous wherever it can, but hopefully some parts of it are understandable to a broader audience. But yeah, it also contains some references if you want to read out about this framework. Okay, so what do we do in this PAQFT? Well, we start with a spacetime, as one does, and I assume it to be globally hyperbolic, meaning that it contains a Cauchy surface. Cauchy surfaces are great. Then I want to specify what kind of objects I want to study. So this is the choice of configuration space. And this configuration space is, for me, the space of smooth sections of some vector bundle. So either, for the scalar field, it's just smooth functions on the manifold. For Young-Mills is Lie algebra valued forms. And for effective quantum gravity, which I also want to play with, is just 2 forms. Okay, and as for dynamics, I use some modification of the Lagrangian formalism, which is fully covariant. So I don't want to abuse the fact that I have a Cauchy surface, so I don't introduce a split into space and time. So I work independent of that relation. So it can be also generalized in the situations where I don't have a space-time structure. Okay, and classical observables. So starting with classical theory, starting with the classical theory, I have observables understood as functionals on the space of configurations. And yeah, from now on, I will drop space-time because it's all working on the fixed space-time. So I'm dropping M from my notation. And now let's talk about localization. So finally getting to the very point of it. So localization of classical observables, of classical functionals, is governed by the support. And here is the definition. Let me just give you some intuition behind it. So I want the support of functional to describe sort of the region where this functional is sensitive to field perturbations. So this is this condition here. So if I take a perturbation which is supported around the neighborhood of some point, then I want the functional to notice, right? So there is a difference between phi plus psi and phi. That is support, and it generalizes the usual distributional support if my functional was linear. And if that support is compact, then F is local in the first sense I gave. So the first notion of locality, localizable in the bounded region. So that takes care of that part of things. And now I want to talk about the second notion of locality. So interactions being local. So now I want to, pose the question, when is F local? When is F describing a local interaction? And everybody knows, okay, the answer. We call functionals local, we call interactions local. At least classically, if we can write this as some function on the jet bundle. So if we can write F as an integral of the Lagrangian density, and this Lagrangian density F depends on the value of the field and its derivative up to fixed order. This order is here, okay, at a point. So that you can write it this way. And okay, I'm going to introduce a silly term. You can also be locally local. So it means that, you have this big space of field configurations, and in that space, you can also have some things like partitions of unity and covering in regions. And it might happen that in a neighborhood of different points in that configuration space, in that space of fields, F can be presented as a local functionals, but with different K and with different Lagrangian density. So you can imagine, this is a bit far-fetched, but you can imagine patching together patching together functionals which depend on different number of derivatives at different points in the space of fields. So that's just, for mathematicians to be slightly more general than the usual. And talking about mathematicians, well, here is a result which on the face of it is just, a mathematical statement, but I think there is something deeper behind it. So in the joint paper with Christian Brodin, Viet Dang, and Camille Laurent, we have shown in a paper from 2018 that this usual notion of locality that we all are used to from physics is actually equivalent to something that looks a bit more abstract, a bit more general. So this is called the Hammerstein property, and it says the following. So if I have two configurations, phi1 and phi3, which have disjoint supports, and then an arbitrary configuration phi2, then my functional can be written as the sum of F at phi1 plus phi2 plus F at phi2 plus phi3 minus, there is a correction because we counted phi2 twice. So if F was linear, this would be obvious, right? So that wouldn't require explanation. Now, the interesting thing is that this is kind of going, obviously it's going beyond linearity, but not far beyond linearity. And this is exactly the property which captures the locality property. So instead of saying that, I can write this function as integral of the Lagrange density, I can just say that it satisfies this funny Hammerstein property. And this property will appear later on also in the quantum world, which I think is quite remarkable. So I'm going to claim that this property has something to say about what does it mean to be local. Okay, but before I go to a quantum, there should be space. Sorry, there's a typo. Before I go into quantum, I want to give you an idea how do we construct these models of quantum theories in PAQFT. So first of all, let me take all multi-local functionals, so sums of products of locals. This is cheap, nothing bad happens. And now on such things, I want to first define classical dynamics. And this is done by means of a Poisson structure, which is covariant. That's again important because I want to work fully covariantly. And it's achieved by means of the Pallas construction, so the Pallas bracket. And here's the definition. I take retarded and advanced green functions for the free theory, and then take, let's start with the free theory, and then take their difference and that I plug in into this formula. So I contracted with the first derivative of the first argument and the first derivative of the second argument. This is the formula for the bracket. And now I want to deform it using my favorite method, meaning deformation quantization. Again, still in the free theory. I want to construct a product on my space of functionals such that in h bar equals 0 order, it's just a pointwise product, honest to goodness product of functionals, of functions. And the first order, the commutator gives me the bracket. So that's what, people I think are comfortable with the quantization should mean, right? Yeah, we want the commutator to go to the bracket. The difference here is that, the difference from the sort of Dirac hat quantization is that we allow for there to be higher orders in h bar when you take the commutator of two fields, two functionals. And let me know, so here's maybe a disambiguation. So when I'm quantizing things, I'm just changing the product, I'm changing the algebraic structure, but I'm working with the same vector space of functionals, which is important because therefore, when I talk about local, non-local, whatever functionals, I'm always talking about the same space. I'm always talking about the same objects, then I throw in various products. So this distinguishes classical theory from quantum theory, is the kind of brackets, products, all sorts of algebraic structures I have, but the observables themselves, the functionals are always the same. So, okay, that was the small comment. And now let me give you the formula for that star product. So, and let me give you an example of, free scalar field. That's the one here. So the field equations are just the wave equation, the usual Klein-Gordon operator. And for such an operator, I can construct, these retarded and advanced green functions. And I can also find so-called quasi-free Hadamard states for the theory. And the choice of a Hadamard state here corresponds somehow to the choice of normal ordering. I don't want to go too much into that construction. This is a bit technical, but what I want you to remember from that is, okay, so I have this family of possible choices of two-point function for these quasi-free states, and they differ. So they have the antisymmetric part, which is given by what defined my bracket, my Fayes bracket, plus some symmetric part. And there are some nice properties that this thing has to fulfill. And then the product is defined as the exponential product for that integral kernel W. So we take, iterated functional derivatives of f and g, and that last step, we just multiply everything together. So this is the formula for the product. And you can see, okay, so this just differs by the symmetric part. So the commutator indeed would give you IH bar times delta contracted with the first derivatives. That was the speed run through quantization of the free theory. And now for the interaction, this is the important bit. This is what I'm going to focus on right now. For the interaction, we want to construct something which we call formal S matrices, which are exponentials with respect, sorry, there should be a V here, that's another typo. Exponentials with respect to yet another product, which is called time-ordered product. And like the rest of the quantization part of this talk, I'm going to talk about how to define, how to construct those renormalized time-ordered products. So sorry, I think I wasn't maybe precise here. So this Tn is just the nth order here. So let me just correct this if I can. Oh dear, sorry. I can probably correct it on the slide so that it's clear. Okay. Okay. Yeah, that's not working. I'm sorry. Okay, I wanted to correct this. Yeah, so this bit is actually Tn, and here there should be V. Okay, I'm very sorry. I have missed that typo. So yeah, so Tn of V tensor n is the time ordered n-fold time ordered product of n copies of V, and then the S matrix itself is an exponential, so it's a sum, infinite sum over these various Tn's. Okay, and to construct that these Tn's, I'm using Epstein-Glaser renormalization. Okay, then I should probably be able to clear these annotations. Okay. Okay. Apologies for the technical difficulties. So how do I do that? So first of all, Epstein-Glaser is an inductive procedure. So it's induction in n. So I construct things up to order n, and then I know how to construct n plus 1. So this is how Epstein-Glaser does things. And at each step of this construction, you have to satisfy a bunch of properties, which are called Epstein-Glaser axioms. And the crucial one is causal factorization property. So this has something to do with locality. So here it is. So if I have V1 to Vk, which are, well, sort of later or space-like to Vk plus 1 to Vn. Okay, so in other words, if there is a Cauchy surface that can separate the supports here from the supports here, then my time ordered product factorizes. So this is the formula. And this has a very interesting consequence for the S matrix. So on the level of S matrices, this gives, again, this funny Hammerstein property. So, but this time it's not with respect to addition, it's with respect to multiplication. So in the image, you have the S matrix for V1 plus V, right? V2 plus V, and in the middle you have to correct for V because you use it twice. So this is very similar to the situation we had in classical theory when I wanted to say what makes a functional local. Now, this property is what makes the S matrix local. And well, local, I here mean satisfying this causal factorization property. Okay, so that's one lesson, that there is this property also appearing in the quantum world. And okay, well, people also impose further properties, further requirements for those S matrices, including the condition at 0. But with that, just with what I said in that slide, I can link this property, this locality in the sense of Hammerstein property to the locality in the sense of Hack-Kassler net. So here's the constructions very quick. I'm sorry, I'm running a bit late. So we take a family of these S matrices generated by local functionals, and we consider those where these functionals are supported in a given region O, and this is the algebra I assign to O. So now we take two interactions which live in different regions, O1 and O2, which are space-like. Okay, and let's see what happens. So that Hammerstein property, now I have V1, V2, which are space-like, and I take V, the one in between, to be 0. So the S matrix factorizes, and because here I can swap on the left-hand side V1 and V2, it factorizes both ways. Okay, so I have these two things. So now if I compute the commutator, so bring one of those guys to the right-hand side, obviously I get 0. And this is exactly the Einstein causality, the third notion of locality that was postulated in the Hack-Kassler axiom. So this kind of links various notions of locality. So there's locality in the sense of locality of the interaction, and there is locality in the sense of causality. My clock tells me I should finish. So if you want to find out more about these various links for different notions of locality, you can look at my paper in JMP from 2019. Now I'm conscious that I'm going a bit over time. So yeah, if I get 5 more minutes, I can say something about non-local observables. Would that be okay?
Yeah, totally okay.
Please, Kasha. Yeah, please take your time to talk about it.
Yeah.
Okay. So non-locality. So now I told you how well this third notion of locality works, but unfortunately I have to break it. So I have to break it because I'm interested in quantum gravity. But let's start with classical gravity the way I did before, start with classical theory. So we have a metric G on some manifold, and observables are smooth functions of the metric. And now I want to work perturbatively, so I split the metric into background and perturbation and assume background to be globally hyperbolic. And now my observables should be, diff invariant. So now I have a problem, because if M is non-compact, and it has to be, if I'm talking about global hyperbolic, then for F, for my functional to be diff invariant, it cannot be local. This is unfortunately contradictory. So I have to use a weaker notion, and I don't want to go too far from locality because I like it. It has worked out great. So I'm using a slightly weaker notion, which is non-local, but with local derivatives. So each derivative at a given point is a local functional, but the whole thing, would be non-local. So this is somehow something which works good with, works well with perturbation theory, because you kind of at each order for each derivative, you have something local, but yeah, you don't have something which, after taking all this stuff together remains local. But this is sufficient for perturbative renormalization in the sense of Epstein-Glaser. So what I told you about, these S matrices and time-ordered products, this actually works for those guys, which is why I'm going to use it. And you can find diff-invariant quantities which satisfy that condition. So let me give you a very brief overview of how to construct those. And if you had my earlier talks, you probably know it already. So I consider first a classical observable. So I take gravity coupled to matter fields, and these are denoted by phi. So collectively, I have G phi as my my variables. And now I consider 4 scalar fields, four scalars actually, 4 scalars, which are constructed from gamma, so from the metric and matter fields. And okay, so they transform under diffeomorphisms as one expects. And one can think of them, one possible interpretation is as a choice of the observer, as a choice of reference frame, which is, however, dynamical, which depends on the dynamical content of the theory. And this is somewhat similar to the proposal of Donnelly-Friedel from 2016. So I think there is a strong parallel there. And now, because I work perturbatively, I fix the background such that these background versions of these coordinates are injective, so they define a good coordinate system. And now I want to stay close to that neighborhood, so I consider, again, everything perturbatively. And I do the following construction. So this is maybe a bit technical, but it's a fun trick. So I use the background coordinates to go to R4, and then I use the general version of these coordinates to go back to my spacetime M. So this defines the map alpha. And alpha is interesting because it transforms under diffeomorphisms by composing with the diffeomorphism, with the inverse of that on the left-hand side. So scalars would transform by composing with the diffeo on the right-hand side. So this is something which can easily cancel how the scalars transform. It transforms, opposite to how scalars do, which is not a surprise, but there's this -1 here. So now if I take another metric scalar or another scalar observables and compose with this alpha, I get something which is diff invariant because this chi -1 cancels the chi I usually have on the right. And these are my observables. So these are my diff invariant objects. And well, another physical interpretation of those is as relational observables, right? Because I use kind of relations between my scalar A and the values of these coordinate fields of these x's. And again, in loops, this is somewhat related to the idea of relational observables as proposed by Dietrich, Giesel, Rovelli, and Thiemann. But obviously, this is a slightly different setting. I'm still classical, I haven't quantized anything. And here are some examples. So I wrote it a bit more explicitly. So now I can take a non-local object like that. I can also smear it with test function. It's all good. It still transforms well because this point x here actually is described by these dynamical coordinates. So everything is invariant under the homomorphisms. And yeah, you can think of it sort of intuitively as having observable A and observer X. So my object FA sort of contains these two pieces of information. Okay. Yeah, and as I said, these actually happen to be non-local with local derivatives, so amenable to Epstein-Glaser normalization. Okay, so I think that is more or less all I wanted to say. So I gave you an overview of various notions of locality and how to break them. In classical theory and in usual setting, I emphasize this Hammerstein property, which actually captures several of these notions. And going beyond locality, there's this intermediate step considering things which are non-local with local derivatives, where Epstein-Glaser still applies, where one can still get a lot done. Okay, and I also briefly recalled the construction of relational observables. That's it. Thank you for your attention and open for questions.
Thank you, Kasia. Thank you very much. All right, we're gonna do as usual with the questions. Please, if you have a question, use the raise hand feature on Zoom, or if you can find it for some reason, just switch on the video and signal visibly. But much prefer if you use the raise hand feature. Okay, we have Rob Mann. Rob, yeah.
Yeah, hi. Yeah, an interesting talk. What happens to this, or that's not the right way to ask it, because have you given any thought to what happens to this if there is indefinite causal order in quantum gravity?
Okay, somewhat. So, like there is a sort of testing ground for these ideas with the causal set formulation, where I like this is actually fine. This whole story if you perturb the causal structure. So you can see how these things behave if you perturb the causal structure. But because the nature of this is, perturbative, I don't think it can easily describe dramatic changes of the causal structure, let's say, from, if you go from Lorentzian to Euclidean signature. So, yeah, I give it a bit of a thought. I think, one could probably do something in this sort of setting of like one usually describes Wick rotation to describe the transition between Euclidean and Lorentzian signature through some complex complexified space. But yeah, I think I would have to maybe make precise what it means to have yeah, these various locality relations for arbitrary causal structures, which is probably your question, right? So you're asking how to understand this locality if my causal structure yeah, is something strange. Is that right?
Well, partly. I mean, I'm thinking of this work by people like, well, Czesław Brutner's program, and you know, what people like Lucian Hardy have suggested, that you can have regions like in quantum gravity, you can have you don't have definite causal order. You can have A before B superposed with B before A.
Yeah, yeah.
And I mean, it seems to me it should be possible to use your formalism to make definite statements about what is and is not allowed. That's really what I'm thinking.
I think so. I mean, you know, this kind of question kind of has, yeah, one has to sort of specify a state which would correspond to that superposition. So I guess it would be a good idea to look at some toy model and try to figure it out. But yeah, it requires a bit more, I think, because I was just talking about the algebras and observables, but for a superposition sort of situation, you probably want to also talk about states, right?
Well, yeah, I mean, and also what I was trying to get a sense of, you know, it sounds, well, it seemed to me that perhaps space-time still had some form of, if I dare use the word, supremacy in what you're doing, that you're formulating QFT. Like, even when it came to quantum gravity, there's this thought that somehow there's always this underlying manifold with the proper structure. And I'm asking, what if you kick the supports out from under that? Or how far can you go?
Yeah, I think the closest to that is kind of studying this on you know, an evolving causal set. So this is one of the things I'm trying to understand how you know, causal set is sort of minimalistic thing in terms of what I'm comfortable with. So you have you know, just points and some partial order relation, and then you can see how that structure evolves and how that, you know, affects the theory. So maybe that yeah, so I don't mind this partial order to change, I think, as long as there is some partial order, you know, or at least, yeah, I don't know. I can think of going to strange places with that, but it's a very good thing to look at.
Okay, anyway, I mean, it seems to me it is worth thinking about somehow. That's all.
Absolutely.
Okay, thank you.
Yeah, thanks for the suggestion. That's cool.
All right, thank you, Rob. Next question, Rick asked for a question, Rick.
Yeah, Kasia, thank you so much. This talk was very enlightening, very clear. But so what I know about HFT, it's very little, and it's only in flat spacetimes. But I am aware that in these cases, it's possible to find different Hilbert spaces representations for the quantum field theory, right?
Correct.
So you didn't say much about that in your talk. Could you maybe just say some words about it?
Well,
About trying
I mean,
to recover states and Hilbert spaces and
the only place where I kind of floated it. Let's see. So that was here. So I talked a bit about, yeah. I mentioned this Hadamard state. So here we kind of, you know, fix a state on the free theory, and fixing of a state here means choosing a quasi-free Hadamard state, which is described by a 2-point function. So like the only sort of information from the state that enters the theory is that 2-point function. And then, okay, so having a state, of course, we can now use the GNS theorem and construct the Hilbert space representation. And then, yeah, so in this setting, if you choose your quasi-free Hadamard state, then on the level of these functionals, you can compute something like expectation values in that state by evaluating your functionals at 0. So from the computational viewpoint, you just make this choice here, and then you compute away. And then if you want to compute expectation values, then you evaluate things at 0. So that's a sort of, easy way to make computations at that point. But of course, the hard work has to be done. Somebody has to give you that quasi-free Hadamard state, or you have to find it yourself if you don't have friends who construct them. But it's known for a large class of theories. So.
All right, no, sure. And also there's this higher order correction in H bar, right? And this actually comes from this exponential there in the end. I mean, I could think of it in this way, right? Okay.
Yeah.
So,
this is here it's very explicit, right? So the H square comes from then the second derivatives and contracted with W tensor 2.
Perfect. And I guess the last question that I have is regarding the renormalizability of the theories you can treat it with this. So it's like all of this surely works for renormalizable theories, but for non-normalizable theories, there's still no progress that can be done by using these sort of methods, or is it?
It still works for some non-renormalizable theories. So you can construct these TNs perturbatively for things that are power counting non-renormalizable, like perturbative quantum gravity, as long as you meet certain word identities which describe gauge invariance. So like you cannot really do much for theories where there are anomalies which obstruct preserving the gauge symmetries. But as long as you can fulfill those word identities, then you can construct these TNs at each order perturbatively. But obviously for non-renormalizable theories, then if you try to sum up that series, then you would get a bit of a mess. But you get a bit of a mess anyway. So, I mean, there's very little known about the summability of that series. I mean, it's known for, like two-dimensional situations, but in 4 dimensions, even in the usual scalar field of gauge theories, things tend to not converge. But in non-renormalizable theories, you would also have like different contributions appearing at each order when you construct these TNs. But it's doable. It's just ugly.
No, but that's very interesting. That's very cool. Well, thank you so much. That was very great.
All right, thank you, Rick. Are there any more questions? So I have one follow-up on Rob's question that I'm not sure if I'll be asking properly anyway, but I'm gonna try. There's a so in the formalism. So maybe Rob can say something about that too, because in the format, for my understanding of when people use or consider superpositions of causal structures in these works that Rob mentioned. Typically, I don't think there's a notion of partial ordering per se, right? As in, like, I think typically just consider, well, we have one particular partial order superposition with another one, right? So it's not that you can, in the time evolution part of it, right? Not in the part about having microcausality or anything like that. But I wonder how that works in the time evolution part of things, right? I mean, I don't think I have a good idea of how to translate this formalism to a case in which you have this kind of superposition of causal structures.
Yeah, I mean, my feeling is that you have to do you have to describe that superposition on the level of states,
right?
Which is something I didn't talk about. So yeah, I will have to think about what sort of states do we want to look at in the toy model, because doing this in the full theory would probably be a mess. But yeah, I'm not sure either. But that sounds like an interesting thing to try.
Yeah. It's also that because again, yeah, because the last part of relational, this relational formalism is more involved than usual. But if you try to do it naively in a way, if I have a manifold, right, that basically considering two different causal structure proposition is certainly on the manifold side. You definitely need to, when you do it by hand, as in like saying I have two manifolds, right, or some two different causal structures proposition. I really don't know how to translate it into a formalized way into talking about QFT in curved spaces, because in the use of at the level of QFT in curved spaces, you need a foliation, and you need to be able to have a Cauchy surface to do Dirac quantization, right? So
yeah, no, but here it's a bit more liberal. You know, you just
right.
you have to you have some algebraic objects, you have some observables that say tell you something about causal structure, right? So I have, you know, in principle, I design an observable which measures the causal structure or something about the causal structure, right? And then I evaluate it in state 1 and in state 2. And they have different things, and then I can see how it, you know, reacts to the superposition of states.
Right.
So, like from the point of view of the principle, it's not completely excluded.
Right.
So to say, I mean, it's something which is in principle doable. But yeah.
It would be super interesting to see it. I mean, I understand when people do it, like in causal set theory, it's usually considered at the level of path integrals. I wonder, but in the formalism that Rob talked about, is typically a Hilbert space formulation for it. Mm-hmm. So it would be super interesting. Maybe you're the person who can actually do it and bring the two things. That'll be very cool.
Now I'm going to think about it.
Yeah. So Edu, yeah, that's basically what I was thinking of. They have their own formalism like that, but I just don't see how to connect it with what you're doing, Cassia. That's why you're right. That's why I asked.
If you could send me like what you think are the main references that.
Yeah, I'll send you an email on that.
Awesome. Yeah, because I'm like more or less familiar with that, but it would be good to have a reading list. Thank you.
All right, so I don't know if there are any more questions. We have time for some, but if not, let's just thank Cassia again. Cassia, thank you very much. Really good talk. Thank you. All right, I'm gonna pause the recording. Our next speaker of the session is Adam Teixeira-Bonfils, and he's going to talk about the first law of quantum field thermodynamics. Adam, the floor is yours. I'll give you a 5-minute warning as usual.
So hello to everyone. What I will be presenting is also published under the same name here. And this is a work that we did with Álvaro Ortega and Eduardo Martín Martínez at the University of Waterloo. And now I'm studying a master in theoretical physics at the University of Barcelona. So let's jump into the topic. First, we'll go through an introduction, and then we will go through each side of the first law in quantum field theory, and we'll end with a conclusion. So let's start. First, a bit of motivation, which is that thermodynamics we can apply to a wide range of systems. So in the start, it was applied to steam engines, and now we can apply it even to black holes. So would you want also to do thermodynamics in quantum field theory? And the answer would be yes, because things like the black hole information paradox or thermalization in the Unruh effect. However, there is a problem, which is that it's not possible to do thermodynamics in quantum field theory. The basic concept of thermodynamics become complicated when you try to apply them in quantum field theory. So what we will do in this presentation is to try to bring the first law, we will bring the first law of thermodynamics to quantum field theory. And just so to start, we will compare the thermodynamics that we will be doing to the thermodynamics that we are used to in the macroscopic limit. So we'll consider a process, and if we were in quantum field theory or for quantum theory, when we measure quantities, we would get fluctuations in them. These fluctuations will come in part from statistical uncertainty and in part from quantum measurements being probabilistic. But in comparison, if we were to the macroscopic limit, these fluctuations would disappear, they would get averaged out. And we would measure single quantities for a given process. We'd always measure the same work or the same internal energy increase. But in what we will be doing, we will have just probabilities of measuring a certain work and probabilities of measuring a certain energy increase. So we will be all the time talking about work distributions and internal energy increase distributions. So where we will apply this first law to give a bit the process and the notation that we will be using is we will be starting with an initial state, an initial Hamiltonian, and apply to them a unitary process U. And this will bring us to a final state where the final Hamiltonian will be this one here. And so with this, we denote the Hamiltonian in the state, and with I, we denote initial, and F, the final. So in this situation, we will have no heat exchange because the process is unitary. And what happens here, the problem is that there is no established or unique definition for neither side of the first law, nor in quantum field theory or quantum theory. So there was a first step in this direction in quantum field theory that was giving a first definition for work distribution. The reference is here. And it was 2 years ago, just. So what we will go now on doing is to give a definition for both sides of the first law and justify them. So we'll start with the internal energy increase distribution. So to give a good definition of it, we will base ourselves on the properties of classical internal energy increase. And we have that it's simply the difference of the final and initial energy. There's nothing new here. And also, since the internal energy is a function of state, the increase will not depend on the path that we take between these states, between the initial and the final states. So if we translate this to a quantum scenario, the quantities will be replaced by averages and the energies with the Hamiltonian. And in the case of this will give us the first requirement, but for the second one, instead of the energy increase, we have a distribution, and we will ask that this distribution doesn't depend on the path that we take from initial to final states. So we have here the requirements to remember them, and we propose a definition that follows both of these requirements, and this definition is given by this procedure here. So this procedure is first on the initial state, we measure the initial Hamiltonian, we get an energy with a certain probability. And then for the final state, we measure the final Hamiltonian and we get an energy with a certain probability. So the energy increase will be the difference between the two energies, and we choose to give that a probability pi times pf. So with this definition, we get both requirements done, fulfilled. However, it happens that the variance with this definition for the internal energy increase diverges in quantum field theory. So, however, we don't normalize it for free scalar fields, the variance. So now that we have a definition for internal energy increase, we will go to work and relate it to the first law. So first, we look at definitions of work distributions in quantum thermodynamics, outside of quantum field theory, so just quantum thermodynamics. And we have that the more widespread distribution is the TPM work distribution. And this is it is defined by the following procedure here, which is basically we measure the initial Hamiltonian and the initial state, and we get an energy with a certain probability. Then to the measured state, the eigenstate of the initial Hamiltonian, we apply the unitary process. And to the result, we measure the final Hamiltonian, and we get a final energy with a final probability. And so the work is the difference in energies, and we choose to take a probability pi times pf. So why is this two-point measurement distribution used so much in quantum thermodynamics? The reason is that the advantages that it has, that has the properties of classical work when the initial state is diagonal on the initial Hamiltonian. For instance, it follows the first law of thermodynamics, and quite importantly, it follows the fluctuation theorems, which are theorems that relate the fluctuations with equilibrium quantities. And these are the Crookes theorem and the Jarzynski equality. And the Jarzynski equality is also related to the second law of thermodynamics. And there are several disadvantages of this word distribution, but the one that will be more relevant to us is that it doesn't fulfill the first law of thermodynamics for general initial states. And moreover, in a more wide context, there are multiple definitions for word distributions in quantum thermodynamics, but none of them reproduce all the properties of classical work. So if this was not enough, there are more problems with word distribution. It is incompatible with quantum field theory because of two reasons. The first is that the TPM relies on projective measurements, but in quantum field theory, the projective measurements, they are ill-defined, and they introduce causality violations and UV divergences. And there is a solution to this that was given with the first definition of work for quantum field theory, that is to use probes to obtain information from the field. And there is a second problem, which is that the Gibbs thermality doesn't work for quantum field theory, but we used it, or it is used to prove the fluctuation theorems. The Gibbs thermality doesn't work because the partition function is divergent, and what we have to do instead is to use a more general notion of thermality, which is the Kubo-Martin-Swinger or KMS states. So to sum everything up, for our word distribution, we want from the side of quantum thermodynamics, the fluctuation theorems to be there, to be proven, the first law here, and the measurement protocol, which is important because in the end, thermodynamics is an experimental theory, and we have been given measurement protocols for all the definitions that we have given up to now. And also for the word distributions, we want them to be compatible with quantum fields. We don't want to use projective measurements, and we want compatibility with KMS states. And what we showed is that there are word distributions that fulfill all these requirements. And these are the three here: the Ramsey scheme, this word distribution, the Lebedev-Marino-Hill, and the full counting statistics word distribution. That they are all given in this, where the graph is given on these references here. And these are all meaningful word distributions in QFT, and in particular, they all fulfill the first law of thermodynamics. So we have the first law of thermodynamics in quantum field theory. However, there was a price to pay for this, which is that these distributions, they are all quasi-probabilities. So now we can apply what we got to an example of quantum field theory, which is a free scalar quantum field. And we will use the following unitary, which is defined here with this operator, that is a combination of the operator of a field and its conjugate moment. And for simplicity, we will take this operator here, the simpler one here, which has only the operator of the field with a smearing that localizes it in space, and with a switching that localizes it in time, and a coupling constant. And also, besides this process, this unitary process, we will start with the thermal state of the field, so a KMS state, and with beta marking the inverse temperature and this marking the state. So what we got from here is that the three word distributions that are meaningful in QFT that we gave before, they all coincide on this situation, and they give exactly this result here. So this is a non-perturbative result, this is exact. And here we denote the F for the Fourier transform. This is the Fourier transform with respect to the mu parameter here. And it includes directly the switching and the smearing, their Fourier transforms. This still also refers to the Fourier transform of them, and the temperature also influences the distribution. So from here we can get the averages, and we can see, as it must, because we showed it, that it coincides with the internal energy increase average in average. And this is the result. This is the quantity that it gets. And moreover, we have also, for the variances, that if we take the variance of the internal energy increase and we normalize it, it becomes equal to the variance of the work. And they give this expression here, which moreover depends on the temperature. And so the sizes of fluctuations for work and internal energy increase, they are both the same in this situation. So finally, for the conclusion, we will sum up everything. Just first, we saw that we want to do thermodynamics in quantum field theory, but it's not possible right now. And what we did is to provide the first law of thermodynamics with quantities that were meaningful on both sides of the equality. On the one side, there was the internal energy increase, which had the average that we expect from classical situations, and it is path independent. And on the other side, we have the work that fulfills the fluctuation theorems, and it's compatible with QFT. It was defined by probes, and the thermal states that we use for it are Keim states. Also, finally, we use this to give an exact and non-perturbative work distribution for a unitary process in QST that it's localized in space and time. And there we found also that the size of the fluctuations for work and internal energy increase, they both coincide. And with this, we finish. And I thank you all for your attention. And if you have any questions, I'll be glad to answer them.
Thank you very much, Adam. Are there any questions? As usual, please use the raise hand feature. I don't see any questions. Oh, there's one by Thales, by Rick, sorry. Rick, go ahead.
Yeah, so as far as I understand, you were able to actually provide this first law, but like based on these probes, right? So essentially you're using detectors like what we've been talking about the whole conference, essentially, not only, but as well, to define this law. And the question is whether these definitions would work in curved spacetimes as well, because the detectors that we use here, they are suitable for any QFT in curved spacetimes as well. So is there any restriction regarding the spacetime where you're building your quantum field theory, where it's defined, or is that general in this sense?
It was general, yeah. There was no restriction on the spacetime, so I guess it could be used in a general spacetime.
Okay.
So if I may say so, you can even use this formalism to check about work that you have, because you're changing the background. So you perturb the spacetime background, and because you have a quantum field in there, the quantum field is going to work against or in favor the deformation of spacetime. So those are things that we're looking into. And there's a lot of interesting questions that come about with different spacetime backgrounds having something like a first law, and even more interesting, a second law. Which is work in progress.
Yeah, I was about to sort of give this idea or to propose something like this, but yeah, it's good that you're already thinking into this.
Are there any more questions? Hands or anything? Right, Adam, maybe I can ask two questions. One is so people use the TPM formalism in quantum thermodynamics as they go to you know, a work distribution for quantum thermodynamics, right? It's the most popular one. So you don't talk much about failure. I mean, there are two things that it cannot do, but what would happen if we insist on using TPM? I mean, I can like try to brute force my way and use TPM, right? But what are the problems I would face if I do that?
Well, so we use the TPM.
Yeah.
Well, in the process, so the TPM it's defined based on a process where you have to obtain it, you need to measure the field through projective measurements. Then if you had to literally perform this, it would be impossible.
Right, I mean, I can try to do it anyways. I mean, like, might not have a cavity, might not have a case where I can get away with Gibbs states for sure, which might not know, fill in a cavity, for example, and I can get away with Gibbs. And then I say, okay, I'm going to use TPM. So the problem that you have, right, that you said is, oh, you violate causality by doing so. You're not being compatible with the relativistic nature of the theory. You violate locality and causality. So the key point to say is, like, are any of the results equivalent? Are there cases where the results are the same as using a proper distribution, or is it just completely different? See what I mean?
More or less. So
do they coincide in any case or not?
Yeah, in cases where if you were able to apply them, if you were able to perform the TPM, you would get the same answer for initial diagonal states as the distributions that we were considering in this talk.
Right. All right. Thanks for that. If there are any more questions, let's thank Adam again. Thank you for the great talk, Adam.
Thanks.
All right. Welcome to so we're in there for the next speaker. We have Alessandro Leite Ferreira Jr. I mean, butchering your Portuguese is remarkably difficult for a Spaniard, even though it's very easy to understand. It's very difficult to pronounce. You have too many vowel sounds for us. So he's gonna talk about probing thermal fluctuations through scalar test particles.
Okay, thanks very much, Eduardo and Rick, for the opportunity to be presenting here today. And okay, so this work was done in my master's at Universidade Federal de Itajubá in Brazil, under the supervision of Professor Vitor de Laurenti, and in collaboration with Camargo and Ribeiro. So here we have the archive number if you want to take a look. And what I am interested in is to investigate the stochastic motion induced on an interacting particle due to the change in the background quantum field. So this phenomenon was proposed originally by Ford and Yu in 2004. And in the original proposal, you had an electrically charged particle on the electromagnetic vacuum. So it stood still there, and then you introduced a perfectly reflective boundary. And due to this introduction of the boundary, you have some dispersions on the particle's velocity. So this is indeed an interesting vacuum effect. However, it is more interesting because we can have negative dispersions in the velocity of the particle, which is related to sub-vacuum effects. That is, these quantities that are classically positive defined can become negative in the quantum field. So then the general case of a massive scalar field in the arbitrary spatial dimensions was studied by Camargo et al. In 2019. And in this work, I want to investigate temperature effects on this case of a massive real scalar field in the spatial dimensions. Sorry for the dogs. Okay, so, and I think the most remarkable result, and I want to stay, maybe the thing that I want most to stay with you today is that I want to show that increasing temperature can facilitate the detection of this subvacuum phenomenon, which is a counterintuitive result we obtained. Okay, so moving forward here, just introduction show the results for the electromagnetic case. So here we have the dispersions on the velocity. We have a divergence when tau over zeta equals 2. That is a round trip of the photon from the particle to the boundary and back. And we can see here that it can have negative values for these dispersions. Moreover, these divergences are linked back to some idealizations of the model, such as the perfectly reflective character of the boundary, the point particle, and also the suddenly appearing of the boundary. And we will be addressing these divergences by treating the system in a more realistic setting, that is by introducing a switching function between the background states of the field. So in the model proposed here, the boundary and the thermal state will be turned on smoothly. So we have a switching function modeling this smoothly transition between empty space and the other state of the background field. Here I have some results taken from the Laurent et al. Using switching functions. So here, when n is higher, we have a more abrupt switching, and we can see that the spikes are greater. But when n gets lower, as the switching is lower, the effect almost disappears. Okay, so moving on, as I said, we are interested in the real massive scalar field that have arbitrary number of spatial dimensions, and in the presence of an infinite Dirichlet's wall at x1 equals 0. So here we'll be using the Hadamard propagator, the Hadamard function in our results, the renormalized Hadamard function, which is conveniently divided into 3 contributions. So we have first here on the right-hand side, the modified vacuum contribution. Then we have the pure thermal bath contribution that would be present without the boundary, minus what I call the mixed contribution, that is the boundary contributions when temperature is present. So, and I will divide my results into thermal, that is the effect without a boundary, and the boundary contributions. Then the model. So I want to have a non-relativistic scalar charged test particle coupled to the background scalar field. So we have here the Langevin equation, and some idealizations that I'm working on is that I will neglect any back reaction effects, and that the dispersions on the position of this particle can be negligible, so that it will stand still in a position x. So then for the vacuum thermal equilibrium, the average of the velocity is 0, and the dispersions is just the average of the squared velocity, which is given here for a sudden transition, turned on at t equals 0 and turned off at the interaction time, tau. But as I said, I want to treat a more realistic system in which I have a smooth transition between the empty space and the thermal state of the field or the presence of the boundary. So for that, I will use a switching function, which is normalized to have so that the interaction time remains equals tau. So the fluctuations are now given by equation 5. Okay, moving further, the choice of switching function, I will choose 2 because this one here, the first one, F1, gives us a really nice closed expression. However, its switching time, which is a very important parameter, grows with the interaction time. So this function not suited to start the late time regime, as then the switching time would be infinity, would grow with the interaction time, and we have no switching at all. Because of that, I will introduce another switching function. I will talk about a little later. Okay, so here's some plots, so you can see the switching function, how it models the transition. So I will use here n equals to n, and not investigate several values of this n here, because it was already done in previous articles. So n equals to n gives a good value because we have here a smooth transition, but it also reaches a plateau, which we want so that when the interaction is fully happening. You can see here that if n was equal to 1, we would never have the fully interaction. So we never reach 1 with the switching function. So, okay. As I said here, the Fourier transform and the other switching function I will be using to investigate the late time regime. So the switching function is very useful because here the interaction time and the switching time are completely detached. And so I want to stress also that I am using 2 different switching functions, but when I give the interaction time and the switching time, which are the parameters in a physical situation, the physical system is completely defined and the results are the same. I will just be using different switch functions for convenience. Okay, so calculating first with F1, the first switch function. So we have this nice closed expression And I will start just with the pure thermal bath contributions. So I'm studying the dispersions due to the background thermal field in a thermal PMS state. So I have here the expression and some plots. Here for one spatial dimensions, we can see that we have a spike and then it oscillates around its late time value. These oscillations are due to the non-Hugasian character of the massive fields and when D is even. So the non-Hugasianity is that the Pauli Jordan function does not vanish for time-like intervals. That's correct. And we can see here that when going to infinity, to have the sudden transition, but when we do not have the sudden transition, the results are a little more suppressed and it decays with the interaction time growing, but that's because the switching time also grows in this switching function, for this choice of switching function. Moving on for two spatial dimensions, nothing much more to see. We have the oscillations due to the non-Hugasianity, and for three spatial dimensions, we can plot for the massless field. For the previous ones, we could not because we had then infrared divergences. And we can see here that for the massless field, as we have a Hugasian field, there is no oscillations, and the dispersions are way greater. As the mass, when the field has mass, it has more inertia, and because of that, we need more temperature so that it can fluctuate. Okay, moving further, I think that the main result of this work is to study the boundary effects on these dispersions. And as I said, I want to treat them separately. And my reasoning is that we can, in a physical situation, always remove the thermal contribution from our results. So if you imagine, I don't know, some experimental setup, we can do the experiment without the boundary. So we have some signal and then do the experiment with the boundary and then subtract this signal so that the thermal part is subtracted from our final result, and we would see only the boundary contributions and then on the final screen. Then moving further, the calculations are almost the same. We have here also with F1 and the vacuum are just the mixed part over 2, and of course with L equals 0, we have no summation. And we have here the graphs for 3 spatial dimensions, here n equals to n. And here we can see it really is the most interesting result, that when we increase the temperature of our system, the subvacuum effects gets higher. So we have here more negative values for the dispersions. So we can see here the black is for the vacuum case, beta going to infinity, and then we have this temperature increases a more negative value for these dispersions. Also here for the perpendicular direction. Here are parallel and perpendicular directions to the boundary, to the infinite Dirichlet's boundary. And you can see here that they get negative more or less in the same time, tau. So that near tau smaller than 2 here, these both negative effects add up, and we have negative, also a negative kinetic energy for this quantum contribution. Okay, and this is very interesting because if one would measure an effective temperature amounting to these dispersions on the particle velocity, it would be less than the KMS temperature of the background field. Here, varying the mass, so we can see here when the mass increases, the temperature effects are suppressed, and we have here in the dot dashed red line only the modified vacuum contribution and the non-Hugasianity of the field here. So the oscillations increases. Finally, as I said, I want to investigate also the late time dispersions. That would be the residual dispersions when tau is going to infinity. And for that, I have to use the other switching function because then the switching time is completely detached from the interaction time, and I can set the interaction time going to infinity. So here for the pure thermal contribution, for the mixed contribution, for the modified vacuum contribution. And here we have some plots, and I'm plotting the dispersions parallel and perpendicular to the plate with the switching time. So we can see that as the switching time grows, these dispersions are suppressed. And we can see here that the boundary contributions are always negative in the residual dispersion. So we can have a negative dispersions not as a transient effect, but as a residual effect in our system. The term is, of course, always positive. And we can see that we can have, even in the boundary plus thermal contributions, so if they are both turned on at the same time, we can have a negative residual dispersions for this total contribution, which is very interesting also. And moreover, further, I have also investigated the distance behaviors of these dispersions, because in the original case, with all the idealizations, we have also a divergence at the boundary, a usual divergence at the boundary. And with the switching functions, of course, it is regularized. And I want to investigate also how is the behavior of this effect as the boundary is approached. So here I have some plots, and it can be seen that the divergence at the boundary are completely cured. You can see also that in the parallel direction, the dispersions at the boundary does not depend on temperature. So also interesting. But I think that the more interesting for a physical setup for a possible, I don't know, experiment is to investigate the dominance of these effects near the boundaries. So for that, I define this quantity eta here, which when eta is greater than 1, thermal effects dominate, and when eta is smaller than 1, modified vacuum contribution is higher. So it was understood that as we had the divergence at the boundary, the modified vacuum contributions would always dominate as the boundary is approached, but with the switching function, with the regularization, we can see that thermal effects can also dominate. So here I plot this dominance factor at the wall when x going to 0 and at late time. So we can see when the interaction time, when the switching time goes to 0, we have the divergence. So the modified vacuum always dominate, of course. And when the switching time increases for lower values of the mass, the thermal contribution starts to dominate for some values of the switching time. And as the mass increases, we can see that modified vacuum always dominates at the wall, dependent of the switching time for higher masses. Finally, I want to I plotted here so this dominance factor as the wall is approached. So deep in the book, thermal effects dominates, of course, but we can have some interesting interchange for some values of the mass. Here for m beta equals 0.8, we can see that thermal effects also dominates at the wall, but we have a region in between the bulk and the wall in which the modified vacuum dominates. So this would be an optimal region for a possible experiment or something of this sort. Finally, I want to address very quickly some assumptions I made. So we have used idealized boundaries. However, if one would introduce some realistic boundary, this would introduce another cutoff in addition to the one introduced by the more realistic treatment of a smooth transition. However, if this cutoff frequency was higher, would be higher than the frequency introduced by the switching function, the results we obtain here would remain completely valid. Have used also Dirichlet's over Neumann's boundary condition. If in Neumann's boundary condition were used, the effects would have been very different, because Neumann's boundary conditions change by an overall sign the modified vacuum and the mixed contribution. So we would have very different results. Also, we have supposed that the dispersions on the particle's position was very smaller than the particle's position. So that was addressed by Ford and by De Laurenti in some previous articles for the electromagnetic field, which has a very similar expression with the massless scalar field, and it was shown that this assumption is okay. So we have a regime in which this is valid for the regime for the interaction time, and as the massive scalar field has a dispersion that's always less than for the massless field, I'm assuming that this also holds for our case, but should be investigated more closely. And at last, the back reaction due to this particle emitted radiation was also investigated by Ford and by De Laurenti et al. It was shown that not only that the back reaction effect can be of the same order of magnitude of the effects that we are calculating here, but the direction in which the radiation is emitted by the particle as it goes from an empty space to the space in the presence of a reflected boundary is very well known. So we know the characteristic of this radiation, and it can be detected in a real experiment and then subtract from the final signal. Moreover, this back reaction effects must be and will be more carefully investigated for the thermal case, because then we can have thermalization of the particle with the background field. But I don't think that changes the main result we have here, that the subvacuum effects increases with the increasing of temperature. So in summary, we showed that subvacuum effects are present even at finite temperatures and at late times, and also that in the absence of a thermal bath, not a fundamental absence, but a more practical one. So in a final signal of an experiment, in our case, temperature increases subvacuum effects, which facilitate its detection. So very interesting result. Also that thermal effects can dominate over the vacuum near the boundary for some switching times and for some masses of the field, and also that the mass can create an interesting pattern of domination as the walls approach, an interesting interchange pattern in this dominance. So some references, and thank you very much for listening. That's all.
Thank you for the talk, Alex. Questions,
Thanks.
please, again, as usual, raise your hand with the raised hand feature. Okay, Rick, go ahead.
Hi, Alex. I was a little puzzled by the fact that you get the negative value for the expected value of the VI squared, right? Yeah. So do you have like a hand wavy, like sort of like physical explanation for why that happens? Like just simple words trying to I don't know, so that I can grasp the physical concept of having that as a negative number.
Okay, so I think that the more physical way to understand it, it's because we can have in most of quantum states, we can have negative values of the energies. In fact, there are some theorems that show that any operator that has any real operator that has zero expectation value on the vacuum can have negative expectation value. So in some quantum states, we can have negative energies, and this is the case. So due to this negative energy, we can have some negative energy flux going to the particle, and then we have some negative dispersions. It's very bit counterintuitive, but you can think that as a counter effect of the usual spreading of the wave particle. So in the free particle, in the free quantum particle, we would have a spreading. So this negative dispersion would prevent this spreading of the free particle. You can see here also from the Greek function, the subvacuum effects come from the first term here. So we take out the free vacuum, the Minkowski contribution, and we have this quantity that can be negative.
All right, thank you. I mean, it doesn't, it's not 100% clear for me still, but we should talk about it later, maybe.
Okay, sure.
All right, thank you, Rick. There's another question by Albert Rhoda.
Yes, in fact, it's connected to this, not for this particular problem, but something similar. We analyze and we discuss a similar effect in a different context for cosmological perturbations, but it was very similar also in connection with an approach that that Larry Ford was also doing for that calculation. So we did a full quantum field theory calculation and basically showed that you have to be very careful. You have some Hadamard function, some noise kernel, depending how you, that characterizes the fluctuations of your environment that is inducing, or in this case, the field. And one has to be very careful because that is a 2-point function that in general is, has a regular part, but it's in general a distribution and has some, you have to be very careful about the coincidence limit. You have singularities there, but it's actually well defined as a distribution. So if you actually do it carefully, exactly the same kind of thing was happening in some of those calculations that Larry Ford and collaborators had done. They found things that were supposed to be, squares of things, expectation value of squares of Hermitian operators and things like that, that should be positive, and they were finding a negative result. Instead, if you actually took into account contributions that, that were related to the subtleties of this distribution, so not just, not carefully regularizing the coincidence limit. Really, you can calculate the distribution function properly. And then when you do it like that, you see that you have some extra contribution that exactly gives you a positive contribution. And in the end, the final result is positive. So you have, of course, then a comparison between different cases when you vary some parameters. But the important thing is that you recover what you expect, which is that when you take the expectation value, of Hermitian operator square or a positive operator and so on, you do get a positive quantity. And that's something that we discussed with Larry Ford at that time. And they agreed in the end that, so I can afterwards, if you want, send you the reference. That's a different application, but I suspect that something very similar might happen here because the structure is very similar. So your noise kernel or the 2-point function for your field might be slightly different here. For sure, the dependence on the temperature, but most likely the divergent part comes from the vacuum. Well, you have maybe some cross terms here, but there for sure you found that when you properly take into account this as a distribution and calculate it properly, then the result in the end is has no strange properties. When you have expectation values of things that are positive definite, you get the positive result. So I can send you the reference afterwards if you wish.
Okay, I would like that. Thank you very much. So yeah, I think that also when I say things like, for example, that the expectation value of the kinetic energy can be negative, I'm neglecting any classical contribution that would appear also. So, for example, we can have an interaction between a classical interaction between the particle and the boundary that would increase the velocity of this particle, and we have some positive classical contribution, so that we would not have an overall negative kinetic energy, for example.
Yes,
and
in fact,
I don't know if I understood that. Okay, so
yeah,
because
in
of
addition,
I understand that we have. You can say it. Sorry.
No, I was just going to say that, in fact, when you look at these things in detail, you can do it in such a way that you also include, the way we call it is that we call the induced fluctuations. That is basically what you're focusing on here, induced by the environment or the field in this case, that is interacting with the particle. And then if you really did the quantum mechanical treatment of the particle, you would have what we usually call the intrinsic fluctuations that the particle itself has, because it's, quantum mechanical particle, and it has its own, fluctuations. And then you can actually see that when you do a detailed calculation, you typically get, well, you do get two contributions that, contribute to fluctuations of properties of the particle, like the velocity here, for example. This would be a little bit related to your, when you mentioned at the end of your talk, terms that depend on the square of the initial position and things like that. So, but a detailed treatment where you treat on an equal footing the particle and the field, or the two subsystems, the two quantum systems that interact, you would see that you have contributions that are induced by fluctuations of the field that we usually call they are induced fluctuations, and then you have what we call the intrinsic fluctuations that come from the fact that your quantum mechanical system, the particle in this case, is quantum mechanical itself, and it has also fluctuations. So if one wants to have a detailed calculation, you have, or you do a pure quantum mechanical calculation, you see that you recover this structure when you get the contributions that will correspond to induced fluctuations that will be very, very closely related to what you had here. And then you have these additional contributions. So that's another aspect also that plays a role when you look into these more, in a full quantum mechanical treatment, and then you can identify the different contributions.
Okay, thanks. I think I understood. I'd like to see that.
Yeah, I'll send you afterwards. Yeah, I can send you afterwards a couple of references where you can see that.
Thanks.
Right. Thank you, Albert. Any more questions? Before going to have one of my own, I had two questions. One of them was related to that. Actually, Albert, Thales asked about it, and Albert more so. I was really puzzled how you get something that should be, right, the expectation of a positive definite operator cannot be negative. And I was wondering where that came from, but I think it's been discussed already. There's another one there we have, there's a very similar in scope, right, work that I have with a collaborator, Pablo Rodriguez Lopez, that we published in 2018. The difference there is that we consider an atom-like unruly detector structure, and we do compute the covariant force on the detector, right? So, but the back reaction, what the force that is in the context of the dynamical of the quantum friction and dynamical Casimir effect and so on. And it's very similar in scope, and some of the results you showed do match. I mean, the expression analytical even match closely some of the things we got. I was wondering if you can comment on the relation, if you know about it, and if not, I mean, maybe that's something to look into, because it'd be interesting to discuss the similarities and differences, right? Because you consider a charged particle, and the difference is we consider an atom a dipole, if you want, right? It's fully interacting, and how the internal structure of that atom affects the force. It looked to me that some of the expressions were very similar to our gapless limit when you have no internal structure in the atom. That's why I was wondering if you can comment on that.
Okay, yes. As I said here, we have used just a point particle, so we don't have a gap, but also the interaction here is a little bit different because this particle would be charged, so we not interact as a dipole. So if you have a dipole, as you said, let's imagine the electromagnetic case. When you have a dipole, it would the force would be the gradient of the electromagnetic field. Here is just the electromagnetic field.
Yeah, but we do a scalar approximation too, in which we couple a monopole to the field. So in that particular case, it's the gapless case would be reduced to that kind of interaction, I think, right? Because it's linear coupling to the scalar field. A monopole does become a charge, right, if you don't have internal structure.
Okay, sure. Yeah, so I think that it would be the same. So if you take a gapless detector and the wave function localized enough so that the expectation, the derivative goes out at the expectation value, you have the same result.
Yeah. I can send you the link to that article. Yeah.
Please.
Yep. All right. Wonderful.
To see that.
Thank you, Alex. Anybody else
have
any more questions? All right. If there are no more questions, let's thank Alex again. Thank you very much.
Thanks.
I'll pause the record. Right. The final speaker for this session is Abhishek Sahu, that's going to talk about sabotaging correlations between qubits coupled to quantum fields. All right. Floor is yours.
Thank you, Eru, for the introduction. And hello, everyone. Top of the morning to people from who are joining from the Americas, and good afternoon, good evening to people from across the Atlantic and beyond. As Edu mentioned, today I'll be talking about sabotaging correlations, which is a variant of the various entanglement harvesting or correlation harvesting related things that you might have seen in this conference already. So without much ado, let me just try and introduce the motivation for our work here. So we know, we are all well aware that quantum fields contain correlations between time-like and space-like regions of the space-time. And as you might have seen various times in the course of this lecture series, that it can be used for performing several kinds of quantum information tasks, such as quantum energy teleportation and entanglement harvesting, etc. In particular, today we'll be concerned with entanglement, or in general, correlation harvesting, which considers taking two quantum systems, generally called detectors, and tries to couple them to space-like separated regions of space-time and try to harness the entanglement stored in the field itself. Um, in recent times, entanglement harvesting has been studied quite extensively, and various protocols have been proposed which use entanglement harvesting as their basis. And as we are moving towards actual physical protocols trying to use entanglement harvesting, it is worthwhile to consider the question of how secure such protocols can be. In particular, if we can couple two detectors to a field and try to harness entanglement or correlations, um, what if there can be several other third parties that can also interact with the same field, and probably malicious quantum systems? And what happens to our correlation in that case? Can they sabotage it effectively, or can they attack our protocols? So these are some questions we need to consider. And to be adequately able to answer such a question, one often needs to consider a setting where there are an arbitrary or multiple detectors connecting with the field, instead of just two detectors, which normally is the norm in such calculations. So this is exactly the motivation for our talk, for our work, which when Edu and Irene, we got together and started working on, turned into my bachelor thesis project as well. So we study various correlations harvested by, say, targets Alice and Bob in the presence of third parties, which we call interlopers. And our main result is to show that these correlations can be exactly and very effectively cancelled by even a single interloper detector. Please keep in mind that we're not trying to do a very general description of considering an arbitrary number of detectors with field, but our motivation is to just try and understand what kind of interesting ramifications uh, the presence of multiple parties can have on correlation harvesting, which we usually ignore. So we'll be using several assumptions, and so we just want to show a particular example of how interesting effects interlopers can have on correlation harvesting. Um, so this is a schematic that you might want to keep in mind. So we have Alice and Bob in presence of several other interlopers who are trying to interlope our correlations. Okay, so let me move into our setup. So our harvesters are two-level systems, which are modeled as unroot detectors. And I'm sure you might have seen this Hamiltonian several times in the lecture already. The main assumption we make is that we consider in general n such detectors which interact with a scalar massless field according to this unroot Hamiltonian, and we take all of these detectors to be co-moving. So we can always find a inertial frame of reference in which all the detectors are at rest simultaneously. Uh, so there is a smearing function of these detectors about the center of mass x nu, and there is a switching function which helps us um, switch on and off the interaction. Now, with this Hamiltonian, we can generate interaction unitary, and by taking a time ordered exponential, and further we calculate the state of our detectors and the field by doing a unitary transformation. And to find the state of the detectors, we just trace over the field degrees of freedom. Now, we want to do a non-perturbative calculation in this case. And as you know, that it's often difficult to calculate the interaction unitary exactly, even for a single detector, let alone a multi-particle system that we are considering here. So we make several simplifying choices. The first and the big one is that we consider the switching function to be delta-like, and they capture the limit of strong but instantaneous or fast coupling of a detector with the field. So we assume that we can say that the detector almost couples at time ti, and since all the n detectors couple at different times, we can always, without loss of generality, assume that there is an ascending order in time in which they interact with the field. So much for being able to do a non-perturbative calculation. We actually lose the privilege of uh, harvesting entanglement in such a scenario, because there is a no-go theorem that prevents entanglement harvesting per se in when we are using delta coupled detectors. A general proof of that is shown in this paper here by Peter and Johnson and Edu, etc. Um, Nevertheless, we can harvest other forms of quantum correlations. And as you'll be seeing later in the talk, I'll be talking about harvesting mutual information, quantum discard, etc. And then to make the calculations easier, we choose an appropriate basis. So instead of just operating the 0, 1 or the ground state, excited state basis, I take a sort of rotated basis, which you can think of as the plus minus basis in a way. So I call it the S nu basis, where S nu has plus or minus 1 values. All right. So due to this assumptions, we can write the interaction unitary in this nice fashion. We can write them as a product of unitaries ui, where ui acts on, or u nu acts on the detector nu and the field. And because of the choice of our basis, this u nu also takes a particularly interesting form. You can see that it actually becomes a controlled unitary, with one part acting like with one part seeing what the detector nu is in which state, and based on that it operates a multimode displacement operator on the field here, which has a multimode amplitude S nu beta nu k. The beta nu k you can think of for the moment as just a function of the wave vector k, which depends on this Fourier transform of the spearing of our detectors and the time of their coupling, the center of mass, etc. We also assume that the detectors start in a ground state and the fields are in a coherent state. And because of this product nature of unitaries and their controlled unitary, and since each of the individual unitaries is a control unitary, we can nicely depict our interaction with the detectors and the field through this quantum circuit. As you see, we start with the detectors in the ground state here and the field in a coherent state. And one by one, we make these unitaries interact, act on this state, and finally we obtain the final state of all the detectors and the field. So far we have just considered a general scenario. We have like n detectors without really making the distinction of which ones are our target detectors and which ones are the interlopers. In principle, we can choose any two of them to be our targets and all the others to be the interlopers. But to make our final statement easily approachable, we consider the first detector to couple to be Alice and the last one to couple to be Bob. So like in my previous example, we take detector 1 to be Alice and detector n to be Bob, and all other detectors are considered as interlopers. It is also useful to introduce this function Tij, which is a function of like parameters of detector I and detector J. You can think of it as an inner product of the beta functions that I introduced before. And they have a real part zeta ij and a imaginary part psi ij. And you can think of them as functions of this the distance between the center of mass of detectors I and j, and also the time of their coupling, the difference in time of their coupling. All right, now that we have introduced some definitions and quantities, we can just simply take the trace of the detector field state we found earlier, and we can trace over the field and all the interloper degrees of freedom to find the density matrix of Alice and Bob. So we get this ginormous expression here, but the cool fact to notice is that the interlopers enter this expression only through this product of cosine terms over here. So for each detector, we have a cosine theta j factor, where theta j is a function of the xi jb. So you see just the interloper and the last detector come into the picture, not Alice. And for each detector, we have a cosine theta j factor. All other factors here, like this theta 0 and this big theta, they are all they all depend on properties of A and B, but the interlopers only enter the calculation through these cosine theta j terms. Now, this has a very interesting, this is the key to why cancellation happens in our case, as I'll show you in the next slide. So for simplicity, let's just consider a single interloper detector, although our results are general for like an arbitrary number of detectors. And so the target detector is in this state, as I showed earlier, with theta I or I denoting the interloper, the single interloper that we have. And it contributes a single cosine theta I term here. Now we can write this above state in the matrix form in our SA basis, and we see that it's in such a form. The interesting thing to note is that these leading block diagonals, which have row 1, 2, row 1, 2 star, etc., they actually, for them, theta I becomes 0 because SB and SB prime are same for these block diagonals. But in the off block diagonals where you have row 1, 3, row 2, 4, etc., SB is actually minus SB prime. And so you have a cosine xi IB factor. All of them have a cosine xi IB factor in common. So interestingly, when I take xi IB to be pi by 2, the off diagonals just vanish. And voila, now that way we have, you see, our matrix becomes a block diagonal form. And since the block diagonals are same, we can actually decompose it into a product state. So the detector state, if we just write it down, it is in this product state form, with the detector A being in this way and the detector B being in a maximally mixed state. And now, since we have a product state of detectors Alice and Bob, there cannot be any form of correlation between them. So whatever form of correlation you consider, quantum discord, mutual information, observable correlators, they're all going to go to zero because essentially A and B become independent because of their product state nature. Another interesting thing to notice is that the detector B is actually in a maximally mixed state. Now, to be in a maximally mixed state, it must be entangled with something, right? But our no-go theorem actually prevents any form of entanglement to happen between any two detectors. So no matter if you consider A and B, or interloper and Bob, or interloper and Alice, at a time, they cannot have any entanglement between them. So that must mean that the Bob's detector is just maximally entangled with some two-dimensional sector of the field. So what exactly is happening here is that, as I showed the quantum circuit earlier, the interloper, when it acts with the field, it sets it up in such a way that when the detector B interacts with the interloper, sorry, the field, it just gets flooded with entropy and becomes maximally entangled with the field. and as it becomes maximally entangled with the field, it loses its correlation with Alice totally. So that is the main result of our paper, to show that how this cancelling can occur. But all of this, as you might have noticed, boils down to the fact that whether xi IB can be pi by 2 or not. So to demonstrate where how it can be, how xi IB can be pi by 2, or any odd multiple of pi by 2 for that matter, we consider the example, we consider a very specific example of a smearing function. We consider the smearing function to be a hard sphere. So inside in 3+1 dimensions, so inside a sphere of radius sigma, our smearing function is constant, and outside we consider it to be 0. And you can visualize the interloper and Bob or any two detectors as such. So for the hard sphere smearing function in 3+1 dimensions, we can calculate xi IB exactly, and we plot them as a function of the spatial separation between the detectors and the time, and we get a plot as such. So the interesting thing to notice is that this plot has a maxima here. And so the first thing we want to do is to try and make this maxima greater than pi by 2 at least, so that xi IB can be pi by 2 at some values. As you can see here, we make, so xi IB can be pi by 2 for wherever this plane intersects this graph. And so what we do is just calculate this maxima and set this to be greater than equal to pi by 2, which gives us a constraint. Now this constraint dictates that the interloper has to couple beyond a threshold coupling, which is set by inverse of the coupling strength of Bob's detector. And the threshold is like proportional to the radius over Bob's coupling strength, and into a factor which is of order 1. The second interesting thing that we notice is that the xi IB for the hard sphere is non-zero only within this thin strip, uh, which turns out to be the region with mod x minus mod t to be less than 2 sigma, and it is 0 elsewhere. So this region actually turns out to be the region where the two detectors, the interloper and Bob, have some partial time-like and partial light-like connections between them. So let us try to see what kind of positions the interloper can be placed at so that the cancellation can happen. So we take this situation here with, say, detector A located. I have taken a one-dimensional kind of model here, or one-dimensional toy model for this situation, where so this rectangular bar here denotes detector A, and it has a certain length which denotes sigma, and these blue lines indicate the regions, the partial time-like connection, which have partial time-like connection with detector A. Similarly, we take detector B to be at some position x equal to 10 and time t equal to 5, and we mark the partial time-like past of the detector B. And the black lines that you see here, the V-shaped lines, they are actually the points where the interloper can connect so that it can sabotage the correlations between A and B. And as you can see that they are in the region where there is they are in the partial time-like past of detector B. So yeah, so this partial time-like contact between the interloper and the detector also seems to be a necessary thing. So while all this is true for our specific model, we can also generalize this result, and we show in detail in the paper that we're preparing that firstly, this threshold condition can be very easily generalized to a general case for general smearing in n dimensions. And at least for 3+1 dimensions, we have shown that as long as the smearing function is compactly supported, we have to have some time-like or partial light-like and partial time-like connection between the interloper and Bob so that the cancellation can happen. Now that I talked about how cancellation, we can cancel correlations, it's also beneficial to look at what kind of correlations in fact do we have in our example. And we calculate these 4 measures of correlation actually: the simple observable correlators, which are just the correlations between local observables of A and B. We calculate the mutual information, which is a measure of total correlations, both classical and quantum, between A and B. We also look at these things which are so-called classical correlations, which measure the maximum information that we can get out of one subsystem by making measurements, local measurements on the other one. And the difference of the two, which is called quantum discord, which is thought of as a measure of the truly quantum correlations that exist within, quote unquote, between our detectors. So the two main dependencies of the detectors, of the correlation on the various parameters of the detectors is the coupling strength, which is something that we can always modulate, and also the spatial separation or the time of interaction of the detectors with the field that we can see. So here we have plotted all these various correlations versus the the product of coupling strength of Alice and Bob. Bear in mind the fact that for these 2 parts, we have assumed that there are no interlopers. We just want to look at the trends in correlation between just Alice and Bob. And we see that at low coupling strength, all these correlations go to 0. And they reach a maximum and then they reduce, which is not surprising because if the detectors hardly couple with the field, then of course their correlations are going to be small. And if they couple too much, they are just basically flooding the field itself with too much noise, and hence they do not have a lot of correlations. And so there is a sweet spot so that we can choose to maximize our correlations. And all the correlators actually, all the correlation measures, they behave in the same way, as you can see. And we have plotted it for various choices of the spatial distance, spatial and time like distance. The second trend we see is between the various correlators and the spatial and the time separation between the coupling of the detectors. And again, we see that all the correlators actually vary in the same way. So the correlations are maximized when there is some partial light-like overlap between the 2 detectors. Which is not surprising because in this region they can exchange actual quanta and communicate through the field. But in 3+1 dimensions, we know because of strong Huygens principle, the communication happens only on the sphere of the wavefront. So in the time-like and space-like region, we still get some non-zero correlation because of the intrinsic correlations that are stored within the field. They're smaller than when there are light-like separation, but they're still there. And in general, we see that as we increase the spatial and time-like separation between the 2 detectors, the correlation value falls. Sorry. So that's about the correlations that exist in our system. And to conclude, we performed an exact computation of state of an arbitrary number of detectors, and we showed that a single interloper can in fact very effectively sabotage all correlations between our target detectors. We showed that it was necessary for the interloper to couple in the time like past of one of the detectors with a coupling strength above a certain threshold. And when we place the interlopers in a certain specific space-time configuration, it floods the field in a certain way that when the last detectors interact with it, it just becomes maximally entangled with the field and loses any information whatsoever. Now one might think that how does the interloper actually accomplish this task? Like, does it initially Alice and Bob were correlated, but then the interloper interacts with the field and Alice and Bob lose all correlation. So does the interloper steal any correlation that Alice and Bob had? But in fact, we see that no, that is not the case. We show that we can show that in fact when we are approaching the cancelling limit, like if we try to vary the interloper's position and take it towards a position where the cancellation happens, near that regime, it is possible to show that if we set some parameters properly, there are situations where the correlations between Alice and the interloper decrease, and the correlations between interloper and Bob decrease, while the correlations between Alice and Bob also decrease. So that way one can show that the interloper in fact does not rob Bob of the correlations. It just, in a way, it is sadistic, if you can think of it that way. And all the correlations are actually stored in form of the entanglement between Bob's detector and the field. So that's an interesting fact to see. Other than that, we also can probably look at possible usage of this kind of a cancellation. While it can be used to sabotage useful correlations and like model attacks on protocols through this kind of a cancellation, but in some situations where unnecessary correlations or spurious correlations may arise between our quantum systems, we can also use our cancellation protocol to cancel those spurious correlations that may arise unnecessarily. So that's it for my talk today. And I just want to give a shout out to the people who I worked with, Edu and Irene, and also the unofficial fourth very important member of our team, the Zoom app, because this entire work was done on Zoom while all three of us were spread in very different time zones. So thank you, Edu and Irene and Zoom. That's it for my talk today. Thank you for listening. And if I may say this, yeah. Thank you. I'd also like to thank the organizers for organizing this talk under these challenging circumstances, and also giving me the opportunity to talk about my work to a very wide audience of RQI enthusiasts. So thank you for that.
Very well deserved, Abhishek. You got to talk because you do good work. All right, so we can open the floor for questions now. Please put your hands up for questions, if there are any. Okay, we have one. We have Rob. Rob, yeah, go ahead.
Yeah, hi, thanks. Yeah, I thought that was an interesting talk. I'm just wondering, at the end, you looked at discord, but you didn't look at entanglement?
Yeah, we did not, because there is no entanglement in our situation.
So there's nothing to see in that case. Okay.
Yeah. So there is this no-go theorem that...
oh, yeah, because you have delta switchers.
Exactly.
Yeah, sorry. Yeah, you're right. So what if you relaxed the delta switcher and went to some finite range of switching? What do you think would happen? That was my next question.
Yeah, that's an interesting question. And in fact, that is something we are going to try next. That instead of taking delta switching, we want to consider like a general switching function. But again, in that case, we won't be able to do a non-perturbative kind of calculation that we did in our case. So we'll have to look at perturbative effects and see whether the cancellation still persist. So this is work for future. We haven't done it yet, but I think at some limit, if we squeeze the correlations or the switching functions and limit them to a very compact region, we can still probably see the cancellation.
So,
Okay.
so maybe if I may say on that, one evidence that may be the case too is the way the correlations are cancelled, right? In these non-perturbative limits, what the interlopers are doing is putting Bob in a maximally mixed state, which is kind of a good clue that it's going to kill everything you have. I mean, of course, we don't know yet in a case that we have finite switching, that we're going to look into. But yeah, it's good evidence that this is going to carry to a case for extended interactions. Yeah, it's kind of interesting because the interlopers kind of set the field up to boycott. It's like kind of the interloper is pushing the field in the right way to really sabotage Bob. I said, I'm going to flood you with entropy. That's the kind of thing that's going on here.
Yeah, I see the point. Doesn't Bob have any protection?
Yeah, actually, I mean, we have that threshold condition, which says that the coupling strength of the interloper has to be inversely proportional to Bob's coupling strength. So Bob can, in fact, just lower its coupling strength very much so that it makes it difficult for the interloper to interact, to couple with the field, right? I mean, more coupling strength means more energy that has to be pumped. So Bob can reduce its coupling strength while Alice increases its coupling strength too much so that they still manage to get some correlation while making it difficult for the interloper to try to cancel it. So that is one kind of protection that Bob can have. But in general, the Alice and Bob are very much helpless. Like they cannot, because the interloper changes the field itself and they just cannot really do much.
So maybe you can talk about that. So how much knowledge, like, can the interloper do this independently of what Alice does, or how much knowledge does the interloper have to have about the setup, about Bob, or maybe you can comment on
Yeah,
that.
exactly. So the interloper actually doesn't have to have any much knowledge about Alice at all, since we saw that in all our calculations it was just between interloper and Bob. So no matter what Alice does, that doesn't matter. The interloper can just look at Bob's position, and I mean, as long as it knows where Bob is and what time it's going to interact, it can situate itself properly within partially time-like, in the partial time-like past of Bob, so that it can sabotage the entanglement. So Bob can probably simply just delay their correlation or their coupling time to get so that the interloper is out of the sweet spot and it cannot sabotage it anymore.
That's like in the Matrix dodging bullets, though. If you can do that. now the one thing that you keep saying is time-like. I think it's better to say causal contact, right? Because in 3+1D, it's actually light-like, not time-like. You need, the interloper needs to be light-like, at least some part of it with the detector.
Yes, yeah, that's a good point. So yeah, when I say partially time-like, it means it's partially time-like and partially light-like.
Or totally light-like. I mean,
totally,
in 3+1D, there's no time-like signaling because of strong Huygens. So again, but it's like that. If the interloper can shoot you, right, it can boycott you. That's the thing. If it can signal to you, it can actually boycott your correlations, and there's very little you can do.
Yeah, but again, that is something we showed for 3+1 dimensions, and it's kind of difficult to show it in n dimensions, but yeah, our proof is for 3 dimensions at least as of now.
I don't see any reason why it would not work in high dimensions. Yeah. Good. Thank you, Rob. Are there more questions? All right. If there are more questions, then let's thank Abhishek again. Thank you very much for the talk. And also let's thank all the speakers of the session. Thank you all. They were great talks today. Thank you. Before we leave for the day, just a reminder for those of you in Europe. Well, I mean, if you're here, probably means that you already knew, but I say it anyways. We said in the email, we'll say it again, but North America changed to DST. So the effective shift to Europe is 1 hour less until 2 weeks time. After 2 weeks time, Europe will change. And then we'll be again at the same shift, but just keep that in mind for the next session that we start. For those of you in Europe, we start 1 hour later. Sorry, 1 hour earlier than usual. Other than that, thank you very much to everybody for coming here. And I'll see you in the next session. Until next week, bye-bye.